Okay. All right. So last time we talked about number in different bases, right? And if you remember at the end of the class, what we were doing is we were trying to divide by the base, repeated division by the base, right? Keep dividing it, right? So I'm going to pick up from there because just to give you a better perspective, what's going on there, how the division algorithm plays in the trick. So I just wrote down this stuff earlier so that my thoughts together. So repeated division by the base. So this is what we did last time. I'm just going to make sure you understand what's going on here, how the division algorithm plays. So let's say I have this number 345. This is base 10. I wrote down base 10. If I don't write anything, that means it is base 10, right?
Right.
And let's see how this base 10 comes out, all this number 345 by division of 10. So let's divide 345 by 10. Can you divide 345 by 10 and write as a division algorithm? So 345 divided by 10, how many times it goes?
34.
34. What is the remainder?
5.
So that's the first one. So I'm using the division algorithm. So 345 divided by 10. So red one is the divisor. And then I get a remainder 5. Is that right? What is the quotient?
10.
What is the quotient?
Oh, 34.
34. Because you're dividing by 10, right? And if you can, as I said, that turn on your video so that I can see each one of you working. Thank you. So I divide by 10. So now the quotient is 34. What I do next is divide the quotient by 10. So quotient is 34. So this is what I mean by repeated division by the base. So take the quotient, divide by 10. How many times 10 goes to 34?
3.
3. And remainder is?
4.
4. And then what I do next? What is the quotient here?
3.
3. So I have to divide 3 by?
4.
3 by the base.
Oh, that's 10.
10, right? But how many times 10 goes to 3?
0.
0 times. Right?
Mm-hmm.
And the remainder is?
3.
3. Now, if you see from the backward, what do you get?
3, 4, 5.
The remainder, which is 3, 4, 5. That's what we're supposed to get, right?
Mm-hmm.
3, 4, 5. I just wanted to show you that this also works for division by 10. So the base 10, this works. And you can see each step I'm using division algorithm, right?
Mm-hmm.
And this is also Lashwanda. Lashwanda last time said, hey, last number is always going to be 1. And I say, not necessarily. The problems probably I work out is 1 there, right? Lashwanda? So,
Yes, I see.
so here you have last number is 3, right? Because last number is 3 because the starting number was 3, right? So this is how the division by the base goes. So I just show you for base 10, which we don't have to because we already know 3, 4, 5. But if you have to convert any number to any other base, then this division by the base will work very, very fine. So let's work out another example. So I have 3,167, which is in base 10, and I want to convert in base 8. And I'll be doing repeated division by 8. Okay, so let's get your calculator with you. Because this time I'll be dividing by 8. So let's use the division algorithm. 3167. And you want to divide by 8, right? And write
Yes.
down the division algorithm. So the question is, how many times 8 goes to 3167? How many times?
395.
395. So 395 times 8, what is the remainder?
7.
7. Okay. Asia, you are with me? Okay, good. So as you see that 395 times 8 plus 7, that's the divisional algorithm.
Can you scoot the paper over just a little bit?
Over,
Yes, please.
okay. That's what you mean?
Yes, thank you.
Okay. Don't worry about on the cutting side, right on. Don't write anything from there. Just the things we are doing, just write those out, and then we'll get there. So, Asia, what I do next? Next one, what I do? Give me an idea. What I do next?
What do you do? The hundreds place?
Yeah, but place, don't worry about the place, but what I do next? What is the question here?
Repeated division by 8. I mean, oh, convert.
No,
into
yeah,
base
we know
8.
the problem, but the next step is, what is the quotient here?
Convert into the base 8.
Yeah, so you divide quotient by 8, right? So you take the 395 and divide by 8, next step. Just like each step you're writing down. Last time I was not writing down anything, but this time I thought that, okay, writing down will clear your concept. So I take 395, divide by 8. Is that right? 49 goes with 8. 8 goes to 49.
Yes.
And the remainder is,
Three.
what do I do next?
Divide 49 by 8.
Yeah, divide 49 because the quotient is 49. Divide by 8. So 6 times 8 plus 1, right? Which is 49. Am I done or I have to continue?
You gotta continue.
What is the quotient here?
6,
You have to divide by
8.
8. So it's 0 times, right?
Mm-hmm.
If the quotient is less than the divisor, so always it goes 0 times, right? Right?
Yeah.
So I am done now, right?
Yeah.
So what is the number in base 8? So you read from the
bottom up.
so this is what reading backward, that's the what you written there. So reading backward, you get 6137. And that's your answer, right? So I'm showing you how to convert from decimal to any other base. And this case is base 8, right? This will work the way I'm working, exactly the same way it will work for any other base. Okay. Sometimes you worried, I'm sure Deshani worried all the time that how do you know this answer is right? Right? You say, I said that this is in base 8. How do you know this is the answer is right? So let's check. So this is the best thing. So that means checking means convert the base 8 to the base 10, which is the decimal system. So let's check this answer. When you check the answer, what do you do? So you start from the backward, right? 7 times 8 to the power 0, 3 times 8 to the power 1, 1 times 8 to the power 2, and 6 times 8 to the power 3. Right?
Mm-hmm.
So this is I'm checking. So when you check, so this is also you learn how to convert from any base to the decimal base or base 10. So this is how you convert. So when you convert any base to decimal, so you do it again backward, 7 times 8 to the power 0, 3 times 8 to the power 1, and so on. And then when you work this out, you get 3167. Right?
Yes.
So that means you can always check your answer whether you are doing it right. It's good. So both way you can learn. So basically you have to convert a decimal number to any other base or any other base to decimal. Both way conversion, right? And in the same example, when you check, you are doing it both ways, right? And it makes you happy, right? Hey, this is the right answer. Okay. Okay, let's do another example. So this time I'm going to do it in base 16, which is called hexadecimal number. If you are doing in base 16, how many digits you will have?
10.
Base 16.
Oh, 15.
Base, whatever the base is, that will be the number of digits, right? So the digit will be 0 through 15, right?
No,
Base,
it got letters in it. I thought.
yeah, so 0 through 15, first of all, 0 through 15, but problem is when you write 11, 12, you can get confused. Is it 11, which is 2-digit 1, 1, or 1-digit 11, right? So that's why what they do, they start from 10. 10 is a 2-digit number. So 10, they say it is A, 11 is
B,
B, and all the way to 15, which will be
F.
F, right? So replace 10 by A, 11 by B, 12 by C, 13 by D, 14 by E, and 15 by F. You have seen in my PowerPoint, so it's nothing new to you. So now can I convert this into base 16? Idea is the same. It will be repeated division by 16. Let's do that on your paper. And you can show me the paper in your camera that this is what you get, right?
Mm-hmm.
Instead of telling me what you got, just show me the paper, what you get. So you are again repeatedly dividing by 16. So that means you have to use the division algorithm, use your calculator. And write down all the steps, and you get your answer. And then you show me, all of you. I don't know why I have only 3 people today.
Do I need to turn my camera around so you can see it?
So what is your answer?
1A81.
1A81.
Mm-hmm.
How many of you agree with this? All of you agree, or are you still working?
So this is what I got so far. I'm kind of confused on this one.
So what is the first step? Can you read the first step?
Divide by 16.
Divide by 16. So how many times? This is right,
Mm-hmm.
Asia?
Yes,
Yeah.
that's what I have for my first one. Okay, but and then when I did it, when I divided the 424 by 16, right?
Yeah.
26.5. Okay, it's just I don't know why that didn't look right to me.
You only take the whole number, like you only take the 26 and then you add the remainder.
Okay.
Yeah. So multiply that 26 point something, right? So ignore that.
Plus 5.
You good? So here the remainder is 10, but 10 is A. So that's why we wrote A. And then last one is so now you're reading it backward, 1A81. That's what you got, right?
Yes, that's what I got.
Did you check your answer?
Yes, I did check it.
Okay, you did check your answer.
Yes. That's what I got.
So this is again from backward, 16 to the power 0, 16 to the power 1, 16 to the power 2, and 16 to the power 3, right? Good? Okay, I think we covered everything. Now you would be able to convert any number to any base, right? Or any base to decimal number, right?
Mhm.
So backward. So I did both way, and very straightforward. But the main ingredient is division algorithm, right? Which you learn, you said 5th grade. Okay. I just sent an email because we are a small class. Either you are a math major or you're a major minor in math. I need to know prior to missing a class, you need to let me know in an email, hey, I'll be missing today. I have something to do, right?
I have a question.
Yeah,
So when we did the repeat division and we got to 26 equals 1 times 16 plus 10,
yeah.
where did the A come from? Or why is the A there?
8 or A. A, you mean, right?
Yes, the letter A.
Okay. See, this is let's say, if I write down, that's what you want to write? Lashamda?
Got you. Okay.
But the 10, if you write 10, you don't know whether it's a digit or the whole 10, right?
Mm-hmm.
So that's why we have, if you read my PowerPoint, 10 is your A. A means 10, right? B means 11. C means 12, and so on, right? Otherwise, it is very confusing. 1, 1, 0. I don't know whether that's a 2 different digit or 1 digit 10, right? Make sense? Yeah. All right. Thank you so much. Any other question? Okay, as I said that I extended your homework due date until 2 more days probably, just because I haven't finished that. So now I'll move to the this week instruction. Just quick question that how many of you read my PowerPoint already? How many of you read my PowerPoint, new PowerPoint? Anybody read the new PowerPoint? No?
Oh, is that the one with the Euclidean algorithm? No.
Yeah.
Oh, yeah.
Okay. So this is the new instruction. So I'm going to start today. It's always good if you have read it earlier, then you can clear your concept while I'm teaching. So that's why I put it up there so that you can ask me more questions. Okay. All right. So today, so this is the new again, I think you learned this in your primary school, probably the elementary school. Prime numbers. You know what? This is the central concept of number theory. We come and learn number theory only because to understand the prime numbers. That's why we are here for. So this is the central concept of number theory. Now, if you look at my papers, I mean, I've written a paper like 2020 on the prime numbers. So the distribution of the prime numbers. So still people are writing because they don't know much about prime numbers. We know the definition of the prime numbers, but not much about the prime numbers. So you can start working on a paper if you have a more information about prime numbers, if you have a different way to think about them, right? Okay. So that's why it's a very central concept of number theory. So, but you know the definition. So there is, you can source the definition.
It can only be, it's only a multiple of itself and one.
So it will be only be multiple of
Itself.
itself and one, right?
Mhm.
So if you say multiple, I can change that language to it is divisible only by one and itself, right?
Mhm.
Our prime numbers are integers, so integer an integer, and of course I want that to be greater than one because one is not a prime number, by the way. So one, if I put one as a prime number, there will be a lot of controversy in later theorems, right? So that's why we exclude one from prime number. Even it looks like one is divisible by itself and also one, right? So that's why prime an integer bigger than one, which is divisible by either divisible only by one and itself. So it's an integer bigger than one, which is divisible by either one or only divisible by either one or itself. Okay, give me some example.
3, 5, 7,
3, 5.
11.
Asia, give me a few. You unmute.
11.
11. Lasanda,
Yes.
huh?
Also 7.
Say it again.
7.
7. Okay.
7, the number 8.
So these are example, right? So you can look at little bigger one like 43. How do you know this 43 is a prime number? How do you check is 43 is a prime number?
Is it because it equal up to 7?
Say it again.
Is it because it equal up to 7?
What is my equal of 7?
4
So-
plus 3 equals 7?
Oh no,
Oh.
because the definition is divisible by either one or only divisible by one or a number itself, right?
Mhm.
So is it divisible by 2?
No,
Is it divisible by 3?
no,
It is divisible by 5?
no,
Is it divisible by 7?
no.
So you have to really check whether it's divisible by these and these. But the question is, how long you can check, right? When do you stop, right?
Right.
Okay. So we'll talk about that, how to determine a number is a prime, right? So we'll talk a little bit more. But so 43 is an example of a prime number. If a number is not prime, so prime number we usually, because again, lazy mathematicians, prime numbers we usually call as prime, okay? So prime numbers, instead of saying that you say prime. So if a number is not prime, then it is called, what is that?
Is it composite?
So given a number, it is either a prime or a
Composite.
composite. There are two ways. Okay. These are the things you learn probably elementary school. I'm redoing it anyway. Okay, Asia, give me an example of a composite.
I'm trying to write just a second. Oh,
Okay, let's write it out.
4.
So it's a 4
Examples
because,
would be like 4.
yeah. And then,
5,
huh?
5.
Why 5?
No, not 5. 6, 8.
6,
8. These are all divisible by 2.
9.
How about this one?
You can also do 9.
Yes,
How about this one?
Yes.
yes.
Because why?
It's divisible by 5.
And 7, right?
Uh-huh.
So it's not
And
divisible by 1
7.
and 35 itself. There are more divisor of it, right? Other than 1 and 35, right? That's why it is composite, right? Make sense?
Mhm.
All right. Cover this one.
I think that's a prime.
Prime,
Yes, I believe so.
or you believe?
I think so. I'm not positive about it.
This is not an even number, so so it is not divisible by 2, right?
Yeah.
Let's divide by 3. Can I divide by 3?
No.
Hey, even not give me the
Yes, you
answer.
can. I think you can.
Yeah. How many
It's
times?
divisible by
Oh,
3,
yes, you can.
37 times.
Yeah.
You can. So it is
37 times.
So that tells you what?
It's composite.
Is a composite because
Composite.
it is divisible by 3 other than 1 and 111, right?
Mhm.
Right. Okay, good. So that's why you need to read then it will be easier for me to explain more better in the sense that you know stuff and then you have some question. So this is the this is the fundamental theorem of arithmetic, and you know the theorem are way back. So what it says, every integer bigger than 1, so I want the bigger than 1, can be expressed as a product of powers of pi. So do you understand the statement of the theorem? So that's the theorem. Every integer, again, bigger than 1, so I'm not talking about 1, anything bigger than 1 can be expressed as a product of powers of prime. Let's look at examples. And it's easy to see from the example. 120, right? Can I divide 120 by 2?
Yes.
I left with what?
60.
6. Can I divide 60 by 2?
Yes.
I left with what?
30.
30.
Can I divide 30 by 2?
Yes.
What I left with?
15.
15, and 15 is 5 times 3, right?
Yes.
Mhm.
Okay. So I break 120 into small pieces of primes, right?
Mhm.
How many 2's are there?
3.
3. So 2 to the power 3 times 3 times 5. That's what it tells you, this theorem, that every number can be expressed as a product of power of primes. How many power of 2?
3.
2 is a prime, right?
Uh-huh.
How many power of 3?
1.
How many power of 5?
1.
And all of them, 2, 3, 5 are primes, right?
Mhm.
Make sense? How about 180? Let's do that 180.
That would be 2 times 2 times 3 times 3 times 5.
2 times
So
2
that-
times
2.
3
How many twos?
I
I
got
only
3.
got 2.
Right?
That's 90. 90 divided by 2 is 45, ain't it?
Yes.
45 is
45.
indivisible by 2.
So only two twos, right?
Yeah.
Yes.
And then 45, which is
It's 9 and 5.
3 times 3 times 5. Is that right?
Yes.
Yes?
Yes.
Yes.
So which is same thing as 2 square, 3 square times 5. So this theorem is good, right? You can always do that, but these 2, 3, 5s are prime. Make sense?
Yes.
So, this also allow you to find out the GCD between these two numbers. GCD means the greatest common divisor. So greatest common divisor. So here is a 2, here is a 2, here is a 2, here is a 2. Common, right? Yes? And then you have 3, 1, 3 here, 1, 5 here, 1, 5 here. Those are the greatest common
That was
divisor, right?
60.
No more than that, right? So what
Mhm.
is the answer?
60.
60. 2 times 2 times 3 times 5, which is 60. That's one way to find the GCD. Not the best way to find the GCD, but it's one way to find, because this is a lot of computation. Even you want to use the computer to split this into a factors is not easy. So even the computer cannot help you out to find out the factors easily. Small numbers is easy, but you have to think about the very large number, right? Okay, so that's the one of the theorem which plays important role in when you talk about the primes. So next theorem, I'm going to talk about the Euclid. This is one of the very important theorem. So it's done by Euclid. And this is actually done way back, like 300 BC. Way, way back. So Euclid says, and he proved, there are infinitely many prime numbers. So that tells you that the list of primes is never ending, right? So it requires proof, and proof is very simple and small proof. But this is one of the big theorem that there are infinitely many prime numbers. So the list of prime numbers never ends. So for example, as you say, to start from 2, 3, 5, 7, 11, 13, 17, 19. You can keep writing, but you'll never stop, right? The numbers get very, very large, but that could be prime, right? Because it never ends. Make sense? The proof of this theorem is in my PowerPoint. I want you to read that, right? And then ask me a question. And this proof is done using contradiction. To prove, there are two ways to prove things. One is a direct proof, and the other is the contradiction, right? Indirect proof, right? So those who have taken the foundation class, they know that, right? Direct or indirect proof. Indirect proof have two different ways to do it. One is contradiction, and or using the contraposition. So but anyway, so you can look at that, read that, but the statement is there are incredibly many primes. So that tells you there are so many large primes, very, very large. You cannot imagine that how big it could be because it never ends. So there is always a prize to find out what is the largest prime number is known to us. This will be one of the discussion I'll be giving in next one. I already gave 2 discussion board assignment. The second one is now going on, right? And the third one, I'll ask you to find out what is the largest prime known in the earth. If you can find a prime number which is bigger than is known, you can be famous instantly. Okay? So I can send you I'll talk about that in my discussion. That if you can find a number, you can Google it, what is the largest prime number? It will give you the answer. But if you can find bigger than that number, which is prime, or that will be a Shane-Hamilton prime. No, I mean, it's not laughing, right? But you can be instantly famous. And you know, if you see that the history, who are doing it, there are kids like 17 years, 16 years, they're the winner. So,
Wow.
yeah, so you cannot laugh. Okay, any question? As I said, the primes get so large, even like a 500-digit prime. So you can write in the paper. It needs a long paper to write 500-digit prime, right? So again, mathematician, they are lazy. They don't want to write this 500-digit prime number. They use what is called Mersenne prime. The Mersenne primes are the prime which can be expressed as 2 to the power p minus 1. P is a prime, by the way. So some of this large prime number can be expressed as like this 2 to the power p minus 1. So that you don't have to write 500 digits. So if you can express that prime number as a Mersenne prime, then you got it done. But not all prime numbers can be expressed as a Mersenne number. Okay, so this will be always, I'll have a discussion question later on. So going back to the question, as I posed earlier, how do you determine an integer is a prime? Again, I talked about there are a lot of historically what is called they did so which is called sheaf. So using some sieve to determine whether a number is a prime or not. You have in my PowerPoint, it's interesting one, it's easy to read, that Eratosthenes sieve. So that sieve is in the PowerPoint, so you can read that, how to determine a integer as a prime. But here, I'm going to get a gist of that sieve I'm going to explain here to you. So here's the question. Is 167 is a prime or not? What I do first, because I have to divide this 167 by all the primes, right? To make sure there is no factor of primes, right? So, but question is, when do I stop? Because there are so many, infinitely many primes. Do I divide 167 by all the primes, which is infinitely many? Answer is no. You don't have to divide by all primes. What you do is you take the the number is 167, you take the square root of 167. Can you take the square root of 167 and give me an approximate answer?
12.9.
12.9. Okay. So this is what the first thing you do. That then how many numbers, how many primes you have less than 12? Plus 12.9. So how many primes you have less than 12? Give me the
Four.
primes.
5.
Yeah, 5. What are those?
2, 3, 5, 7, 11.
7 and 11. So all I need to do, I divide 167 by these primes, and if it's not divisible by these primes, then it is a prime number. Make sense? If this is not divisible by this prime, then it's a prime number. This is what Sheeb tells you, is Sheeb of Erythronius. So it's not divisible by 2 because it's not an even number, right? Is it divisible by 3?
No.
Is
Yeah.
it divisible by 5? Anything divisible by 5, last digit will be either 5 or 0, right? So it's not divisible by 5. You can divide by 5 and do you get a whole number? No. Is it divisible by 7?
No.
Is it divisible by 11?
No.
Okay, you said that I'm sorry. The
Yeah.
seed is if the number is divisible by one of those numbers, then it is a prime number.
Now, if it's divisible by one of them, then it is not prime because you
Okay.
had prime. Then if it's divisible by other than one and itself, then it will not be prime, right? So if it is not divisible by these, then it is prime, right? And you check. That's a bad thing to check. How many numbers have to check? 5 of them. Some of them are easy to check, right? It's not even, forget that 2, right? So none of them are divisible, right? Divides this, right?
Yes.
Yeah. You can check. So this is a prime number. Okay, let's do a few more. You work this out because you have to tell me what are the primes I have to divide by. That depends on your square root top, right? Asia, what did you get here?
Approximately, are we around one? Yeah, 1 decimal point. 14 point.
Go on, just decimal
14.6.
14.2. So that means everything,
6. 14.6.
yeah, 2, 6, I don't really matter, but
Okay.
so, but below 14, right? So what are
Yeah.
the numbers?
The numbers that's 2, 3, 5, 7, 11, and 13.
The same and 13.
Yes.
You have a one more extra. So now we keep dividing to 13 by one of these. If it is evenly goes, you say, no, it's not a prime. If it doesn't evenly goes, then it is a prime, right?
Yes.
Did you check?
Oh. Okay. It's not a prime
Why?
because it can go into 3. 71 times 3 is 213.
Okay. So it's divisible by 3, right?
Yes.
So it's not a prime. So if it's not prime, what I write?
It's a composite.
Composite.
Sense? Okay, last one. Lasanda. What is this, Laswanda?
The square root of that is approximately 18.6.
So the numbers are here are
2, 3, 5, 7, 11, and 13.
anything else?
And it's not divisible by any of
17.
those numbers.
Very good.
17.
Oh, I thought it said 17, my bad.
Okay.
I'm working and talking to you at the same time.
Does it divide?
347 is not divisible by any of those numbers. No.
Okay. So none of them is divisible by this, right? So this is,
Prime.
so this is one algorithm. I just show you that this is you can always use to determine some number is prime or not, right? Make sense? Good. So we just found out, last question, we basically found out using the SHIB that how do you determine an integer is a prime or not, and that's how you find it out. Number gets larger, your work is more, right? You have to take the square root and you have to know also all the primes below that number, and then you have to divide each one in number by each one of them. And then finally, if it is not divisible, then it is a prime, right? Now, here's the next question. How do you count primes? I want to count how many primes is less than 100, right? So that's the next thing I want to know. How many primes are less than 100? How many primes are less than 200? And so on. So here is the counting function. So I'm going to use a counting function. Some reason or the other, they use what is called pi of x, like f of x, function of x, same thing, but here they use a pi of x. So then if you write pi of x, they know that you're counting prime. But this pi is nothing to do with our real pi, right? It's just a f of x, right? Function of x. What is function of x? F pi of x is equal to number of primes less or equal to X. So this is the definition of pi of X. So number of primes less or equal to X. So that's a called counting function, which is a pi of X. Anybody knows number theory, if you tell them the pi of X, they know exactly what you're talking about. So for example, if I want to know what is pi of 10, so 10, how many numbers, how many primes you have less than 10? What are the primes less than 10?
2, 3, 5, and 7.
2, 3, 5, and 7. 2, 3, 5, and 7 is less or equal to 10. These are the primes. So how many of them are there?
4.
4. So your answer is pi of 10 is 4, right? Make sense? Pi of 20. So next one is Asia, and the next one is Ashwanda. So first you write down what are the primes less or equal to 10 or 20 or 30, and then you give me the number of them.
8. Then it's 8 of them.
8 of them. What are those?
2, 3, 5, 7, 11, 13, 17, 19.
Good. So you can take that list, and then the Shonda you have to figure out after 20, right?
Correct. I want to say the next one would be 23 and 27.
No,
No.
Oh, shoot.
27.
That's 3 and then 9. You right. So boom, 29.
Yeah. So how many of them?
1, 2, 3, 4, 5, 6, 7, 8, 10.
Okay, we have plenty of time. Can you give me here like how many primes less than equal to 10? Almost 40% prime, right? Here. Is that right?
Mm-hmm.
Because number of primes less than 10 is 40. How many here? What percentage? Also 40, right?
Mm-hmm.
This is also 40%. Now this is on less probably, right?
It's about 33%.
Because 1/3, right?
Mm-hmm.
Can you do the 100? It takes a little time. Also, you know all the primes below 100. That's long time, you know.
Wait,
You know,
I'm sorry. How did you determine those percents again?
who was that question? Asia?
Yes.
Oh, just the percent. How many have you? 4 in 10, right? So 4 over 10 is what? 40%,
Okay. 40.
right?
Yes.
8 over 20, again, 40%, right?
Yes. Okay, I get it now. Thank you.
This will be interesting to know. You already have up to. You have it? These are mine. Two is the only even prime, right? So when you look for prime, you just look for odd. And some of the odds are not prime. So these are the entire list of prime less or equal to 100. How many of them?
25.
What do you see here? As the number gets larger, right? Percentage of prime less than equal to that number is what? Getting
Smaller.
smaller. You start with 40%, this one 40, next one is 33, and this is how many percent?
25.
25, right? So as the number gets larger, number of prime less than equal to that gets smaller and smaller. So if you if you go like a million, 50 million, then it will be very rare to find a prime, because this percentage is getting smaller and smaller. So as you go up, primes are very rare to find. So that's why it is difficult to find the prime. There are prime, infinitely many primes, so there will be always a prime, but it's very rare. That's why these whole prime numbers are very obscure. People don't know much about them. They know a lot, but still they don't know much. Okay. I guess best thing to do is stop here. I have like 5 more minutes. Only 3 people. That's why I'm afraid. I drive down there. I drive 50, 60 miles, and then I have 2 people there sitting there. I feel bad, really. Here you have the luxury. You sit home, drink coffee, right? You
Right,
can take a 2-minute break, talk to your mom, right?
right.
Or your friend, but still you can teach, right? Or you can listen, right?
Mhm.
And I'm not going to do anything different than that, but here is more focus, right?
Yeah,
Yeah. In the classroom, it's a big room, your focus gets lost. You look through the window or the door, right? Who is
yeah.
going, right? So that's why I don't want to go there. I can go. I mean, I'll go sometime if it's very sunny, and I'll go there and to just you personally 1 or 2 days. But if this is happening, then I hope they listen my recorded version, the other people.
Do you usually have small classes like this, like of like 7 people?
Yeah, I have a class which I'm doing online. I have a 35 students.
Oh wow.
Oh, wow.
But in math class, these are basically math major or education major, right?
Mhm.
I'll be teaching in a 45 minutes a graduate course, which has 3 students.
Oh wow.
So it's not worth going there, right?
Yeah.
And it's not worth for them to go there in the classroom, right?
All right.
Yeah. All right.
All right.
Okay. If you talk to your friends or classmates, let them know what you did. Okay. I'll be posting anyway the video, right? Recorded. All right. Thank you so much for
All
coming.
right. Thank you.
Take care.